Last time we finished our discussion of abelian and non-abelian gauge theories, and at the very end we briefly began the gravity case. Many things in the gravity case are going to be, the details are going to be similar to many things in the gravity case, the details are going to be similar to they were to abelian, non-abelian gauge theory case, and so we won't have to. There'll be a lot of things that we'll just be able to skip, and indeed we've already described or partially demonstrated the soft graviton theorem, which was just a minor modification of the soft photon theorem. So we already have that behind us. And so our starting point, which we discussed last time, but I will review anyway, is that any metric can locally be written as ds squared is minus du squared times a function u minus some other function which we write as e, which is conventionally written as e to the 2 beta du dr plus gab dxa minus plus a half ua du dxb plus a half ub du. And this, where a and b, I'll sometimes write as shorthand. I'll often you take them to be z and z bar. They're two spatial indices. And this differs from those general 4x4 matrix that you could write down in the fact that there's no dr squared term. There is no du dr dxa term, and so there's three conditions. In general, you get to choose a diffeomorphism allows you locally to set 4 things to 0 because it's parameterized by an arbitrary vector with 4 components. And so in so-called Bondi gauge, one imposes the additional condition that dr times the determinant of gab over r squared is equal to 0. And this simplifies a lot of expressions. The main reason, though, for using this coordinate system, as I described before, is that 99% of the literature on this subject is in this coordinates, and so if you want to compare to the literature, you want to be working in these coordinates. But it does have its advantages. Then the next piece, so far I've just said something about metrics, but we want to study asymptotically flat metrics in Minkowski space. And eventually we're going to be talking about quantum gravity. And in quantum gravity, one of the things that we've understood in the last years is that you want to fix the boundary behavior. And so here we want to fix the boundary behavior at the edges of the space-time to be Minkowskian. But what exactly does that mean, to fix it to be Minkowskian at the edge of the space-time? What are the exact constraints on these different components? Now, there's a huge amount of literature on that, which I'm not going to review. And there are different proposals which all have some basic things in common. They involve different kinds of constraints and gauge conditions, and they may differ in some what is and isn't allowable geometry, but they all have in common that they allow all of the basic physical kinds of configuration, like gravity waves and black holes and so on. And so, and in fact, I think they all agree that the metric has the form. We can now expand. So this is r equals infinity, the edge of this diamond. And I'm going to be discussing Scry plus. So we can expand near Scry plus. So u is going to be a retarded time as minus du squared minus 2 du dr plus r squared gamma z bar dz dz bar. This, of course, is the flat metric, which we've been using all the time in our discussion just of gauge theory on flat space. But now we're going to correct it because we're doing gravity. We're going to consider fluctuations of the metric itself. And the leading order terms are twice the so-called Bondi mass aspect over r. And I should warn you, I have a habit of abusing terminology a little bit and just calling this the Bondi mass because I get tired of saying the word aspect. Though the Bondi mass is sometimes used to mean the integral of this thing. But I sometimes just call this the Bondi mass. And I hopefully be clear in the context. Plus r czz dz squared. So this is an arbitrary function. So this is an expansion in r. So these coefficients don't depend on r. They depend on u, z, and z bar, which are coordinates on Scry. So we're expanding about Scry plus. There's obviously an isomorphic expansion about Scry minus. Plus r c z bar dz bar squared plus uz du dz plus uz bar du dz bar plus higher order terms. Now, this term, for example, has an r in front of it. So in what sense is that subleading? Well, it's subleading because this term has an r squared in front of it, right? So this is a component of the metric on the two-sphere at constant r, but it's subleading relative to this term. And similarly, this would be a subleading, this is also a subleading term. Okay, so now, in order for the metric to be flat, it must be true that not in order for the metric to be flat. In order for the Riemann tensor to fall off like some appropriate power of r, which is a power of r which is weak enough so that it doesn't exclude gravity waves, you need it to be true that uz, in order for it to be asymptotically flat, I think by everybody's definition, uz is equal to dz czz. And one also defines, so if that's not true and you compute the curvature of this metric, then it falls off, the Riemann curvature falls off too fast. Important point is, I have not at this point imposed the Einstein equations. And everything I've said is consistent with gravity waves as well as light waves or other kinds of waves going through infinity. One also defines in this business the so-called Bondi-News, NZZ, which is the time derivative of CZZ. So NZZ is to gravity it's the transverse components. So if we're at null infinity, so Z and Z bar, if we draw a sphere up here, what does it look like? So U is this direction, and we have some waves coming out like this. This sphere here is parameterized by Z and Z bar. So the transverse to the direction of propagation will be Z and Z bar will be the transverse components of the gravitational wave, of the polarization vector of the gravitational wave. So they're spatial components. So NZZ is a gravity wave, and indeed we'll see later that whenever NZZ is non-zero, you have some gravity wave which is passing through infinity, and there'll be some energy loss which will go like the square of NZZ, and we'll be able to see in a moment that the Bondi mass will decrease appropriately, though as so far I have said nothing about the Einstein equations. I also want to mention that U here is retarded time, T minus R, and that a line of constant U looks like this. So if you move in the R direction, keeping U fixed, you're moving in a null direction towards future null infinity. This we already encountered in the abelian case. Okay, now let me tell you what I am conspicuously not saying, and which has been a huge source of confusion in the literature, I think to a large extent settled by Christodoulou and Kleinerman in the 90s, but understood better, is it's not really enough to say what the metric does up here. We need to know what the metric, which is Scry plus, we need to know something about the geometry at the boundaries, Scry plus plus and Scry plus minus, because we don't want to be talking, we want to be talking about physical spacetimes. And so, for example, if we had NZZ equals constant, that would be some infinite energy configuration which had been radiating forever. And so we also want to understand how these fields behave near Scry plus plus and Scry plus minus, a subject of which there were hundreds of papers on before Christodoulou and Kleinerman, almost all of which were completely wrong. So it's a very confusing subject. And we'll explain that a little bit later, hopefully even today. Now, so I think now specifying what I haven't given you here a complete mathematical specification of what an asymptotically flat metric is. I've told you enough of the ingredients of it so that we can get on with our business. I believe that what the part of the boundary conditions that are needed are this part of the boundary conditions are all approaches to asymptotic flatness essentially agree with. When you get to the further subleading terms, which you do need to do, and if we are to delve further into in fact, even when we start talking about superrotations, we're going to need more terms than I wrote here, and it's going to get more complicated. But anyway, I'm pretty sure now that everybody would agree that these are necessary, if not sufficient, conditions for asymptotic flatness. And so we say that GUU is equal to -1 plus order 1 over r. GUR is equal to -1 plus order 1 over r squared. GUZ is order 1. And GZZ is order r. So this is another way of saying what I'm saying up there. I guess actually this seems to be a little more information because this beta up there has to be actually order 1 over r squared for asymptotic flatness, not just order 1 over r. And GZZ is order r. GZ bar Z bar is r squared gamma ZZ bar plus order 1. And GRR and GRZ are identically 0. Okay, so this is the fall-off conditions in Bondi gauge of the metric components. Okay, so that's the definition of asymptotic flatness. But now, and again, I have not yet said anything about the Einstein equations. But now, Bondi-Metzner-Sachs, way back in the early 60s, asked a very, yes, Tarek.
Sorry, last time you said GCD bar was r squared plus order r. Was that a typo last time?
You know, I've written in here order 1.
That's coming from the del r of determinant GAP by r squared, which implies the order r term is traceless.
Right,
So it doesn't
exactly.
exist.
Right. Yeah, so last time was wrong if I wrote order r. When I wrote it down just now, I thought, why does that order r? But right, that's the reason. Yeah. Okay, so they asked a very interesting question, which is, suppose I do a diffeomorphism, an arbitrary diffeomorphism, which preserves these boundary conditions. How many such diffeomorphisms, what kind of diffeomorphisms do they have, and what do they do to the space? Now, the answer they were expecting was that it was somehow something like Minkowski space. In Minkowski space, you have, in special relativity, you have the Poincare transformations, rotation, boosts, and translations, and they preserve exactly the Minkowski form of the metric, and this is asymptotic to Minkowski space. So the thought they had was, if it's asymptotic to Minkowski space, that the metric, there should be some preferred subgroup of all diffeomorphisms which preserve the asymptotic structure, but don't, which preserve the asymptotic structure, but act on the system. And you certainly expect the boosts, for example, to act non-trivially on the system. So you take, if you have a black hole with energy E and you boost it, energy E and momentum 0, you boost it and you get something with non-zero momentum. So you expect some of the diffeomorphisms to act non-trivially. What they were expecting was that they would, out of this story, somehow get the Poincare group. And they would learn that general relativity reduced to special relativity in some infrared limit. And they failed to do that. People tried for years to do this. It seemed like it had to be true that general relativity reduced to special relativity in the infrared limit. I think we now know nobody ever succeeded in it, and we now know why, which is general relativity doesn't reduce to special relativity in the infrared limit. General relativity has a spectacularly rich infrared structure that is just not there in special relativity. And BMS were the first to get a hint at this, though I don't think they understood the full import of what they found. So they tried to make the statement precise. So the way they tried to make the statement precise was they asked, what are the vector fields that leave all these conditions invariant? They might change C or MB or U, but they obey these boundary conditions. And what are they? And let's write them as an expansion about it, infinity in 1 over R. Okay, so now I am not going to quite address that question. I'm going to address a slightly different question, which is just a little, actually a lot shorter to answer, but still gets us to the interesting part. I want to take vector fields with the property that in an orthonormal frame, their components are all of order 1 at infinity. Zeta, that means that zeta u and zeta r are of order r to the 0 at infinity, and zeta z and zeta z bar, so I have a vector field zeta a dA, and generating a diffeomorphism, and they are order 1 over r. And this 1 over r comes because if I were to go into an orthonormal frame at infinity, I would have to multiply these by r. So for order them to be finite in an orthonormal frame, I need this. Now, what this condition excludes is rotations, right? Rotations are vector fields which are generated by vector fields which grow like r at infinity, and boosts which also have components which grow like r at infinity. And these are very interesting things, no less interesting, in some way more interesting. It turns out it's also excluding the super rotations, but I want to, what I'm not excluding is the super translations, which I want to study first. So now what we want to do is we want to look at the Lie derivative of the metric. So if we have a vector field zeta, and we act on the metric, that is, by definition, zeta c dc gab plus dA zeta c gcb plus dB zeta c GCA. And we demand that if we take vector fields and we write out these, we act on a metric obeying this, we want to know if we get a new metric obeying this. Well, that's not very hard to do. So I think I did the, well, I guess I can do them this way. Okay. So if we take L zeta of GUR, that is equal to minus du zeta u. So the metric doesn't depend right, to leading order, GUR is just -1. So zeta A dA of this will be 0. So I only have to worry about these terms in the Lie derivative. And so I find that I get minus du zeta u plus corrections, which are going to go like 1 over r. This term could be of order 1 if these are my conditions on zeta. And then L zeta GZR is equal to r squared gamma ZZ bar dr zeta Z bar minus dz zeta u plus order 1 over r. Then L zeta G ZZ bar is equal to R gamma ZZ bar. Remember that GZZ bar is R squared gamma ZZ bar at leading order, is R gamma ZZ bar 2 zeta R plus R divergence of zeta Z plus R dz divergence of zeta Z bar plus order 1. And L zeta GUU is equal to minus 2 du zeta u minus T2 du zeta r plus order 1 over r. Okay, now we have the simple task of just solving this for zeta. And so this one is very easy to solve. These conditions do not allow an order 1 piece to GUU. We only have an order 1 over r piece. So we immediately learn that, so what is the solution? We immediately learn that zeta u, but zeta u can be any function of z and z bar. Okay, so now if we do that, we've solved this equation. Okay, so now this is such a kind of key moment in the whole story. I'm going to throw it to you to find the next term. I'm going to throw it to you to use these equations to find zeta z and zeta z bar. It's not very hard if you look at the right equation. That's too. I mean, it's not that hard, but I'm just asking for this. So I'll give you 3 minutes to find.
And at this stage, zeta u can be f plus order 1 over r, right?
Yeah, but you don't need to know that for the leading term to get the leading term. Right. At this stage, that could be true, but you don't need to know that to get the leading. I only want you to get the leading term in zeta z.
Excuse me, is it supposed to be L zeta GUU, the first line? Because GUR was -1 plus order of 1 over r squared.
Wait, which formula are you asking me about?
The first line. Is it on the left-hand side L zeta GUU or?
No, it's GUR.
But GUR on the left is -1 plus order 1 over r squared.
That's right, but I'm only working out. I could have kept going here forever. I could have added here more, but I only worked out the leading term in each case.
Right, but then the first piece du zeta u shifts to that -1.
We're trying now to find necessary conditions. We're trying now to find necessary conditions for that these zetas have to obey. I'm not going to.
Conserve the boundary conditions on the left.
Yeah, we're trying to find the simplest necessary condition.
Oh, okay.
Okay, we're not trying to solve the whole thing.
You open it, yeah.
I'm not in class. You're going to work out a little piece of the answer. It's actually not that hard to solve the whole thing, but I don't think it's that instructive to do in class. But all we're doing now is we're looking at we're picking the low-hanging fruit here, which I think gives the conceptual picture of why these vector fields take the form that they do. Okay, so I'll give you 3 minutes to try to find the zeta z and zeta z bar. And actually, I'm going to give you a hint to make it a little bit easier. Oh, yeah, right. So, and we're assuming that zeta z and zeta z bar do not have an order 1 piece. Okay, I forgot that. I think that was more than 3 minutes. So it's pretty. It all follows actually from this equation here. So we know that this term here is just minus dzf. And since the leading component of zeta z, let's call it, let's write zeta z, that's a zeta z bar, is 1 over r zeta 1 z bar. That would be the leading component. This just becomes plus, we'll get a dr of this, we'll turn this into 1 over r squared. That'll cancel this r squared. And we'll get a minus sign. So we get a minus zeta z bar, zeta 1 z bar. So that's easy to solve. That says that zeta 1 z bar is equal to, what did I do with gamma z? Gamma z z bar. Zeta 1 z bar is equal to, I can write it as dz bar f. I raised the index on the dz. As I defined earlier, these dz's are the covariant derivatives on the unit sphere, and I raise and lower their indices with gammas, not g's, so they don't have any, so that all r's are explicitly displayed. Yeah, minus dz bar f, right. And so zeta z bar, so zeta z is minus 1 over r dzf. And a similar calculation would have told us that zeta z bar is minus 1 over r dz bar f. And these terms, and then zeta r turns out to be dz dz f. So the final result, so I've shown you this is necessary. It also turns out to be sufficient. That the final result is that zeta sub f is equal to f du minus 1 over r dzf dz minus 1 over r dz bar f dz bar plus dz dz f dr. Now, of these terms, let me just say this last term is not very universal. It essentially is there because of this condition that up there, that we're keeping the volume element on the spheres fixed. Newman and Unti considered other kinds of formalism where that wasn't quite true. These terms do turn out to be very universal, and in fact they're exactly what these are. Reparameterizations of the sphere at infinity, which go to 0 at infinity, and they turn out to be exactly what is measured in the gravitational memory effect. And of course, this term is also universal. Okay, so these are called supertranslations. So far from finding 10 Poincare transformations, there's an infinite number here. Now, had we not made this undue restriction, we would have found 6 more things, rotations and boosts. And those rotations and boosts don't commute with these supertranslations. If you commute with the they don't commute with ordinary translations. Rotations and boosts don't commute with ordinary translations. So you get all kinds of weird looking things when you start commuting it, and you get a big group known as a big infinite dimensional group known as the BMS group. Now, suppose F is, there are 3 things that we already knew about here. Suppose F is a constant. If F is a constant, then this turns out to be just d by du. And so this is just global time translations, energy. So F equals constant is energy. Now, what is less obvious is if you take F to be any one of the 3 L equals 1 harmonics on the sphere, that this turns out to be a translation. So this coordinate system, of course, is not unlike usual flat Minkowski coordinates. This coordinate system is not manifestly translation invariant. There's a center, r equals 0. And so translations do something complicated to these coordinates. And but it turns out that that is contained in here. In the L equals 1 modes of F are ordinary, what we would think of as ordinary translation. The associated charge will be the ordinary ADM momentum. But there are an infinite number of other charges which are on equal footing with energy and momentum in gravity. Any questions? Okay, so how do the fields transform? So let me write LF as a shorthand for the Lie derivative with respect to zeta f of the Bondi-Metzner-Sachs. Well, if we take the Bondi-Metzner-Sachs and we just find that it translates as f du nzz. So this is kind of a formula we might naively expect. All the other components of zeta are vanishing at infinity, well, except for this one, but the variation of the news, dr of the news would be subleading at infinity. So, so this is kind of exactly what you would expect. In other words, it acts as a translation, a position-dependent translation along the null generators. Let me draw a picture here. So we can think of, we have a sphere at infinity. Let me draw it like this, which is parameterized by z and z bar. And we are familiar with the idea that constant translations along infinity are a symmetry. But now we're doing translations which actually I should, if I'm going to draw this, I should draw the Penrose diagram for Minkowski space in this other way, where you put r equals 0 like this, and then this is r equals infinity, and every point in this diagram is a sphere, except for the origin, which is a point. And this is the sphere at infinity, which I've drawn explicitly. And we translate it at different amounts at infinity, depending on how big the function f is. The magnitude of but the translation that occurs at infinity does not depend on u. F cannot depend on u. That was the first requirement that we wrote down there. Okay, so that's what you expect. But now, if you compute the Lie derivative with respect to f of the Bondi mass, you get something a lot more complicated. You get f du mb, which is the term you expected. But then you get a funny inhomogeneous term, which looks like plus a quarter nzz dz squared f plus 2 dzf du uz plus complex conjugate. And what about czz itself? This is perhaps the most interesting of all the equations. If we take the lead derivative with respect to f of czz, we get that it transforms as f du czz minus 2 dz squared f. So what's funny about this is, did I miss a term?
So dz squared is z.
Oh, yeah.
Oh, the dz dv bar contracted by gamma dv bar.
It's 2 dz's. Oh, so, yeah, it's 2 dz's.
Okay.
Yeah, it's 2 dz's. It's logical but confusing. So what this, and we'll have a lot more to say about this later, what this tells us is that suppose that we're in the vacuum, or suppose that the metric is just that first line there. We're in flat Minkowski space. And we perform a supertranslation. Well, in flat Minkowski space, the news is 0. There's no gravitational radiation. And the Bondi mass is 0. There's no energy anywhere. And this involves the news here and the news here, so the transformation is 0. But C becomes non-zero. Now, you might say, wait a second. How can the space be flat if, so we know that if we take this equation, we set the Bondi mass to 0. This implies, it's surprising if you were just told this, but it's true that if you take this metric and you set czz to minus 2 dz squared f, and you have to change u and everything, and then you compute the Riemann tensor, you find it's still 0. And in fact, it goes both ways. You can show that if the Riemann tensor is 0, that is, the space is identically flat, that the metric must be of the form czz must be of the form dz squared of some function. And of course, cz bar z bar, its complex conjugate. And this is very significant, and we'll have a lot more to say about it. But before we go any further, I want to write down the constraint equation. So far we haven't said anything about the Einstein equation. So let me write down the constraint equations. And what they say is, so in particular, we're interested in the UU component, the constraint equation tangent to, I mean, all the constraint equations matter as we develop this story further, but the one that is important for supertranslation is the G Einstein tensor UU constraint equation. And that says that the U derivative of the Bondi mass, and this is a very sort of famous equation, is a quarter du dz uz plus dz bar uz bar minus TUU, where TUU I'm defining to be 1/4 the square of the Bondi-Metzner-Sachs. So that is what, so in general, in a general curved space-time, it's hard to say how much energy is carried by the gravitational field. But if you're in near flat space, then it is an unambiguous concept, and certainly out at null infinity, it is an unambiguous concept, and we know exactly how much energy was carried by the gravity waves that measured whatever it was, GW09, whatever those that black, that did work moving those things around, moving the mirrors on the interferometer around, and so gravity waves carry energy, and it's unambiguous, and this is what it is. It's the square of the Bondi-Metzner-Sachs, just like it's the square of the first derivative of the metric, just like the electromagnetic energy is the square of the first derivative of the vector potential. But then I'm going to add to this. I'm not going to be insisting that we do pure gravity plus 4 pi g times the limit as r squared goes to infinity, r squared Tm uu, where Tm uu is any kind of light wave, any kind of matter stress energy that passes through null infinity. Now, I am going to allow for this generalization. I am not, at this point, I'm not sure exactly when I need to use this, but I am going to be most of the time, unless I say otherwise, assuming that we're talking about space-times that in the far future settle down into empty flat space, so that there isn't a lot of stuff going on in the far future that we have to keep track of. We're just recording things going through null infinity. Generalizations to that case are possible, but it makes a lot of the equations longer, and it's not efficient to try to do all that on the board. Okay. So now, why did I want to tell you this? Because I want to talk about now solutions of some scattering problem. So suppose we find that, and I think I want to go back to my other way of drawing Minkowski space. Suppose I find that I've solved the Einstein equations, and I find that I have a solution in which a pulse of gravitational waves comes out at this, let me call this the South Pole, and this the North Pole. A pulse of gravitational waves comes out at the South Pole at, say, u equals 6. Retarded time u equals 6. And then at some later time, u equals 1,000. Some stuff happens in here. I don't necessarily know what. I'm just looking at what happens at null infinity. Some later time, u equals 1,000. So far, this may have all seemed kind of formal and not so weird, but it's all about to get really strange. So at u equals 1,000, I find that a pulse of gravitational waves comes out at the North Pole at u equals infinity. And okay, now suppose I take this solution and I do a supertranslation with it, which has the property that F on the south pole is equal to 0, and F on the north pole, or better yet, let me take F on the north pole. F on the north pole equals 0, and F on the south pole equals 994. So that means I get a new solution. I've just done a diffeomorphism. So I've got a new solution. But my new solution has the property, it's the news, which characterizes the gravitational radiation, transforms in this very simple way under supertranslations. So it has the property, the new solution that I get has the property that nothing is happening at u equals 6. And at u equals 1,000, I see a pulse going on the south pole and a pulse going on the north pole. So it's clear from this example that these supertranslations are changing one physical configuration to a different physical configuration. You don't need to compute any charges or do any more work. It's clear that they're acting non-trivially on the phase space. Just like you boost a black hole, you change its energy, you change its energy and momentum, everybody is going to agree that that is something different. So these supertranslations are acting non-trivially on the phase space, and moreover, this solution on the right, since it's a diffeomorphism, if we work out all this stuff, taking importantly into account this term here, we're going to find that if this thing obeyed the constraint equation, that this one has to obey the constraint equations, because supertranslations of solutions, they are diffeomorphisms, non-trivial ones, but they will preserve the Einstein equations. Now, this makes this discussion much cleaner in a way than the analogous one that we had in electromagnetism. In electromagnetism, all that was happening was we were changing phases of things coming out in the North Pole and things coming out at the South Pole. And phases are kind of slippery quantum mechanical objects, and do you count them as real or not, and so on and so forth. Well, I think we argued that the answer is you should, or really that you have to. But it took some doing, and I think that is why, even though the large gauge transformations, as you can now see, are the exact analog of the large gauge transformations we talked of in QED. QED has been around. Well, I mean, they're already there in the Maxwell theory, but you know, QED has been around for 100 years, and nobody noticed them. And the reason is that it's not so obvious. It involves these slippery phases, and people have recently understood what it means to measure these phases, and it's certainly there. But in the case of gravity, it's completely clear that these things are acting non-trivially on the phase space. So any questions about that? Yeah.
So if let's say I sit at the point u equals 6 on the left on the Scry class, right?
And
And I make this coordinate transformation. For me as an observer at u equals 6, nothing really changes, right? Because I just made a coordinate transformation. It shouldn't be different. I mean, like with in the example with black hole, yes, the black hole.
Well, first of all, you can't just make the coordinate transformation at u equals 6 because things which depend on u, things that depend on u are not supertranslations. So you can't just make it at u equals 6, at least not in any simple way. However, it will turn out that energy going out to infinity does induce a supertranslation. So these things do happen, but it's a more complicated discussion than which we will get to. But you can't just make a coordinate transformation at u equals 6.
So like in Abelian in gauge theories, the thing with what we could actually measure were the differences of the phases, right? That's, it wasn't like really meaningful to say that the phase at this point is this. It was meaningful to say what is the difference of phases between different points, right? Is it different in this case?
Well, the sharpest way, right. So that is one thing that can confuse people. But at the same time that all this was going on, there was, and this is we'll talk about this later, but there has been 40 years of discussion of measuring this effect, and it's called the gravitational memory effect. And so there is a very precise sense in which this can be measured, but we're not quite there yet.
But it's meaningful to say.
But I think our starting point, the point of view I'm taking now, is that how do we in this coordinate system, how do we think about? I should have said this. Thank you for asking that question. How do we think about the space of initial data? Well, first of all, if we're on Scry+, we don't want to think, we want to talk about final data, but by time reversal, it's the same thing. Okay, so we're talking about how do we think about the space of final data on Scry+? Well, the characterization of final data on Scry+ would be that you start, and in fact, I think there are still pieces of this problem which are unsolved. But the beginning point of thinking about what that is you start by specifying everywhere on Scry+ the news function as a function of u and z bar. So you specify a free function. That is like saying, in particle physics language, you say when you specify how many gravitons of what polarization, and the fact that it's complex means you're specifying two functions at every point. So at every point you have to specify how many positively polarized gravitons you're sending in and negatively polarized gravitons. That would be the natural way that we would think about the initial data problem. And then you would start with m equals 0 up here, and you would solve this equation. Remember that, okay, you would also have to, and this is the point that everybody would have missed, you would also have to specify CZZ up there. And CZZ would have had to be, in order for it to be a vacuum up there, would have to be dz squared of something. So you specify CZZ up here. You would specify, you start with the mass equals 0, and then you solve this constraint equation. You need initial conditions to solve this equation. You're not just solving this equation. You're also at the same time solving du, that NZZ is du CZZ. So first you integrate this with an initial condition for CZZ to get CZZ everywhere, given NZZ. And then you integrate this to get the Bondi mass, and you're partway there. And the reason I say partway is there's some really interesting subtleties in the subleading terms, which we're not discussing now. And also when I say that, of course, I'm assuming there's no matter coming out. If there's matter coming out, we have to specify that too. And now you assume that every such specification is a different point in the classical phase space. I mean, gravity waves it's just like electromagnetism, out at infinity. They're just weak propagating waves. And we'd say that it's meaningful to talk about their relative times and positions and amplitudes. That would be the starting point. And then the observation of BMS is that there's a group that acts non-trivially on this space. Okay, so let's take our 5-minute break, and then I'll continue. Okay, so now I want to just briefly say that there's a similar story on Scry minus. To be explicit, we write Scry minus, it's plus 2 dv dr, since v is t plus r. And there's a plus 2r squared gamma z z bar dz dz bar plus 2mb over r dv squared plus r czz dz squared plus r cz bar z bar dz bar squared plus, or minus rather, minus uz dv dz minus uz dv z bar dv dz bar plus dot dot. And I believe I've chosen conventions, so you get from that metric to this one by taking u to minus v. And now notice that I'm using the same symbols for these objects on Scry minus that I used on Scry plus. But they have arguments. So CZZ of VZ Z bar is obvious, means that this thing on Scry minus, where if there's a u there, it would be the same thing on Scry plus. Different notations appear in different papers, and I've myself have come to the conclusion that introducing a whole new set of, calling these DZZ, or introducing a whole new set of symbols for the things on Scry minus causes more confusion than it clarifies. So I'm going to use this notation. And as usual, this Z also is antipodally related to the one on Scry plus. Z goes to minus 1 over Z bar, and V is advance time T plus R. Now, obviously, we have the same story. And if we now look, we get a zeta which is exactly is exactly this. except I guess we have a plus here and a plus here and a minus there because we're taking u to minus v. And one finds that, again, LF of NZZ on Scry minus is F dV NZZ. And LF of CZZ is F dV CZZ plus 2 dz squared F. And similarly, and when I looked at this, I was reminded of the fact that this is plus 2 and that is minus 2 up there. There's nothing inconsistent about it. All the formulas, the signs, everything could be consistent. But I feel there should be some conceptual reason that I'm missing why this C is transforming with a minus 2 on Scry plus and a plus 2 on Scry minus. I don't quite understand why this sign was needed, but there it is. And so then we have the constraint equations, which are now dVmb on Scry minus is equal to 1/4 dV of dz uz plus dz bar uz bar. Actually, let me just call this d dot u, dv d dot u, and plus tvv. And tvv is equal to, again, 1/4 nzz plus 4 pi g, the limit as r squared goes to infinity of r squared times t matter vv. I think I neglected to say, of course, if there's a finite energy flux through infinity, since infinity is going at any value of retarded time, since the volume is going like r squared, tvv better be dying like 1/r squared. That is the usual situation in radiation, that the energy density falls off like 1/r squared, the field falls off like 1/r, and so this will be a finite answer. And by the way, if you take that formula or this formula, easier to think about that formula, and you integrate it over any cut, called a cut, any sphere at future null infinity, you find that the integral of the Bondi mass is just given by the last term, because the first term there is a total derivative. And so the integral of the Bondi mass is just minus TUU, which is the famous statement that the Bondi mass is always non-decreasing as you look at it, that it's a retarded time analog of the ADM mass, and it always decreases as you move forward on future null infinity. Okay.
So the sign for TVV is different for TUU because of this change, or?
The sign for TVV, no, TVV is, this is squared.
I think he means in the dV and V equation.
Yeah, I'm just comparing with the DU and D.
Um, well, but that's right, because if TVV is positive, you expect the energy up here to be bigger than up here. So You could have adopted some different conventions, but I think these would be the standard ones. The Bondi mass is increasing along Scry minus to its maximum, the ADM mass, and then decreasing again along Scry plus. Okay, so now we find ourselves in a very strange situation, which the field essentially was in for 50 years. And that is the following. If you look at, there's a lot of mathematical work on general relativity by people like Christodoulou and Kleinerman and Yau and many other important people who studied properties of Yau studied properties of general relativity. If you say to them, Bondi coordinates, they shudder. They don't know what they mean. They don't know why they should exist. They don't, and they will only have a discussion with you about coordinate invariant quantities like Riemann tensors. So the kind of problems that they like to study. So for example, the problem that Christodoulou and Kleinerman famously studied and solved, and it was related to, I'll say more about it in a minute, but let's take a initial data, a space-like slice in some curved space-time. Let's find a solution of the constraint equation, and then study what happens to the Riemann tensor, all the different components of the Riemann tensor, as we go up to null infinity, or we go to space-like infinity, or we'll go to time-like infinity, or whatever. Those are the kind of problems that they study. Now, that isn't enough for us, because suppose we had such a solution in which suppose we had such a solution, we could take any such solution and we could write it in advanced coordinates up here, do BMS transformations on the advanced coordinates, retarded coordinates up here near null infinity where they're suitable, do a BMS transformation, completely change the character of the outgoing data, and get a new solution. And we would do it independently on the future and the past. So finding things which are only involve curvature invariance, finding only the diffeomorphism invariant quantities, is far from solving the problem of gravitational scattering, by which I mean even the problem of classical gravitational scattering. I haven't gotten quantum yet. So in classical gravitational scattering means let's take a point on Scry minus, let's take a solution of the constraint equations on Scry minus and ask the question, what does it solve to on Scry plus? Not only was that question never answered, the problem was never even posed. It was never asked in a way that made any sense. Because according to BMS, you could, given one solution, it would say, okay, there's this symmetry. So BMS did not really they did not think of what they did as some kind of symmetry of the theory. I don't really understand how they thought of it, but they certainly didn't think of it as a symmetry of the theory. Now, what you need in order to have a clearly, in order to have a solution of the scattering problem, is that we're going to talk about in a moment, is that you need to, I mean, among the BMS transformations, among the supertranslation, let's talk, it's nice to talk about boosts, okay? Among the supertranslations, among the whole BMS group, there's also boosts. I didn't show you how they work out to obey those boundary conditions, but it's easy to believe. So obviously, if we boost, if we've set everything up properly, we boost the incoming configuration, it should evolve to the boost of the outgoing configuration. That is intuitively obvious and indeed required by energy conservation. So what is needed is something which we can't have symmetries that act just on outstates and not on instates. We need to have symmetries that act both on instates and outstates, and in other words, things that commute with the Hamiltonian. Those are the useful things, and BMS didn't think they had that. And so I'm not sure they used the word symmetry. I'm not sure how they were thinking about it. Now, what did people do about this? Well, it's hard to make sense of it, what they were doing, but I think that that there were two really big problems. One was that that were kind of went in the opposite direction. One was that Penrose imposed some boundary conditions called asymptotic simplicity. And this isn't quite right, but roughly speaking, asymptotic simplicity implies, now we've got a symmetry here. I haven't talked about the charges, but we're going to construct the charges and do maybe, well, probably not quite this lecture. But asymptotic simplicity roughly implies that all these charges vanish, which is a kind of fantastic reduction of the phase space. And it wasn't obvious that there was any solutions that obeyed Penrose's boundary conditions. And then people proved that there were some families of solutions for which these charges vanishes. And there was some sense that this asymptotic simplicity captured most of what we wanted to know about general relativity, and that extending beyond it to the more general case was kind of technical and trivial. I would say that was completely wrong, and that most of the work in general relativity, I mean, many people understood that most people I think understood that Penrose's asymptotic simplicity was too strong, but still there was some kind of sense that you would understand most things. And there are things like the peeling theorems, which are in every single textbook on general relativity, which depend on this asymptotic behavior, which are wrong in very simple situations, like, for example, the scattering that we just observed in the sky of the two black hole mergers. Whenever you have things coming in from infinity and scattering, it violates asymptotic simplicity. Asymptotic simplicity really means very, very simple. And it doesn't have to be two black holes scattering. If you scatter two protons, you know, that the gravitational field produced by that will violate Penrose's asymptotic simplicity. On the other hand, it was thought that if you let go of asymptotic simplicity, and went for the more general case that this function c here might not be well defined, that n could go like 1 over r. So if the news goes like 1 over r, CZZ goes like log, the energy can be finite. Sorry, start that over. If the Bondi news goes like 1 over u as we go to the boundaries of Scry, the energy can be finite, but C won't be well defined. C will have a logarithm in it. So there were two different kinds of situations that were considered, both of which did not allow for any matching of the BMS at the future to the BMS at the past, and I guess the relativists just didn't feel it was important to define gravitational scattering. Now, okay, so then along came Christodoulou and Kleinerman, and did, again, they never talk about Bondi coordinates, they never talk about any of these things, but they give formulas for components of the news. And the important thing was that they showed, well, their big contribution was, and it's really sort of great work in mathematics and also in relativity, they showed that that they define a norm, and they show that in a finite neighborhood of flat space, that all solutions of the equations of nonlinear equations of general relativity exist globally. That is, there's a finite neighborhood within which you don't make a black hole, and which is what we would hope. Otherwise, Minkowski space is unstable or something. You know, it's hard to, perturbation theory would be bad or something. They showed that, okay, so they showed that, but they did much more. They gave explicit fall-offs. And in particular, they showed that the Bondi news for all in this neighborhood of flat space falls off like 1 over u to the 3/2, which means there can be no logarithms, and that C, this quantity C, is well defined at the boundaries of Scry, which was crucial. This happened in 92 or 93. I asked, when I realized that Penrose's boundary condition and the peeling theories implied that all the BMS charges were trivial, I sent Christodoulou an email, and he said, I said, what's wrong with the, how this is contradicting what you're saying? He said, oh yes, and I explained it in after Lemma 46 in my unpublished lectures in Capri. So, and he sent me a copy. But the world didn't learn about it. But you know, I mean, people understand it. He's a character. People understand it now. But anyway, so that means that C is well defined here. So Christodoulou and Kleinerman show that in a reasonable classes of spacetimes, which do not obey Penrose's peeling theorem, most spacetimes don't obey Penrose's peeling theorem. Generic spacetimes don't obey the peeling theorem. CZZ, if we evaluate it at Scry plus minus, is equal to dz squared of some function c. In fact, I think I usually write this as minus 2 dz squared, just so it's, that makes it very easy to see that this function c just shifts by the supertranslation under supertranslations by F. And so now we can get back to our old tricks. In fact, all of this was done before all the stuff that I've presented so far. Because in this BMS story, there was this very sharp puzzle. Nothing made any sense. QED seemed to make sense. And in fact, we didn't think there could be anything new to be learned about QED. And it made me nervous to think that all of this might also apply to QED, where somebody ought to have noticed it. So now we can impose boundary conditions that the Bondi mass as a function of z and z bar, mass aspect that is, it's Scry plus minus, is equal to the Bondi mass as a function of z and z bar at Scry minus plus, again with the usual antipodal matching. And this is just the gravitational analog. You can verify this condition holds in linear perturbation theory by a Lienard-Vickert type formula for linearized gravitational fields, just like we did for the electromagnetic field. But we're imposing it as a more general boundary condition. And CZZ of z and z bar is equal to, at Scry plus minus, is equal to minus CZZ, z and z bar at Scry plus minus. And then that preserves the supertranslations, F of ZZ, this boundary condition. Now, so before we impose any boundary conditions, we have, a group which is twice as big as we want, a group that acts on the top and acts on the bottom, and has no hope of being a symmetry of any kind of scattering problem. If there were, so you can't have symmetries which act on out states but not in states. So So you see, because of the relative sign between, they're covered up now, but between this and its Scry plus analog, if you have one metric that obeys these boundary conditions, the action of this supertranslation will give you a new metric obeying the boundary conditions. And you can also check that for the Bondi mass. It's a little bit trivial there. And then we get supertranslation charges. If these things are equal, then obviously we have supertranslation charges, which are just 1 over 4 pi g integral over Scry plus minus of an arbitrary function f, gamma z z bar, mb, and that's equal to the same thing integrated over Scry minus plus by these boundary conditions. So now we have, with these boundary conditions, an infinity of conserved charges, and verification that we haven't lost our minds is that if we now write the matrix element, we look at a quantum theory where we have gravitons and so on, and we write Q plus Fs minus S Q minus F, any out state, any in state. That would be the quantum analog of this classical conservation law. This is just Weinberg's soft graviton theorem. And to show that, is 5 pages of algebra. But it's just like the algebra. I mean, it's really just like the algebra. And we did it before we did the QED case. It's just like the algebra for the QED case. So I'm not gonna when I put you through the algebra in detail in the QED case, I promised you wouldn't have to go through it again. But it's the usual thing of taking the plane waves and parameterizing the p's in terms of points z and z bar on the sphere, and so on, and out after a bunch of algebra pops Weinberg's soft graviton theorem. Let's say a little bit more about the conservation law. So we can write the conservation law. Now, we can take these q's, multiply them by 4 pi g to kill this factor, and then integrate over, take q plus and integrate it by over Scry plus. Notice that we get a u derivative of the Bondi mass aspect, which is the thing that appeared in the constraint equation. And so we can use the constraint equation to write that as an integral over Scry plus, and we can equate that to an integral over Scry minus. And what we find is that the integral over Scry plus of du d squared z f gamma z bar TUU. This is the hard part of the charge. Minus a quarter. And then we have du dz uz bar minus dz bar uz plus dz bar uz is equal to the integral over Scry minus of integral dv d squared z gamma z bar tvv plus 1/4 dv dz uz bar plus dz bar uz. Okay, so suppose that we take f. There's an f here. Suppose we take f to be a delta function on the sphere at some point w. Then we can trivially do this integral, and we learn that the integrated energy flux through delta, through the point w, which includes not only a hard contribution from, which is quadratic in the gravitational field strength and in the matter fields, but a soft contribution, a zero mode of a graviton. The energy flux going through that angle will be equal to, the outgoing energy flux through that angle will be equal to the incoming energy flux through the opposing angle. So the geometry really remembers a lot. Remembers an infinite amount of stuff. The outgoing state remembers an infinite amount of stuff about the structure of the incoming state. And so we can think of this as energy conservation at every angle. When f is a constant, it tells you that the whole integrated energy flux is conserved. The incoming energy is equal to the outgoing energy. But far more than that is true. The cumulated outgoing energy flux at every angle is equal to the incoming energy flux at every angle. And you can also see from this how this is sort of writing this as one step towards writing this as Weinberg's soft graviton theorem. If we take quantum matrix elements of this, we're going to get a hard part which is proportional to the energies of the particles, and then a soft part, the soft graviton term, which this, of course, is ultimately a zero mode of some derivatives, z derivatives of the gravitational fields, which all work themselves out in a magical way to be the same factors that Weinberg had. Yes, Tarek.
So is there a restriction on the energy conditions such that you don't, for example, form a black hole and spoil this?
Well, the only I am assuming here that there will still be an exact identity, there will still be an infinite identity if you form a black hole. But when I took this and integrated by parts, I assumed that there was no boundary term up at Scry plus plus. And if there's anything going out at Scry plus plus, I have to worry about that. So, right, so there is a story like this when, I mean, this doesn't assume anything. This is true when there are black holes, anything. But this formula does. We'd have to add a black hole or even massive particles. There would be more contributions to that. Yes.
So it looks like the soft parts can be negative as well. So like, does it mean that soft gravitons can have negative energy, or is there any interpretation of that?
Soft gravitons can certainly have locally negative energy. Now, it's a total derivative, so it integrates to zero on the sphere. So they can have negative local energy, but their total energy is zero. That's the meaning of the statement that they're soft. Okay, that's a good place to stop the lecture, I guess.